friends, students and learners, I am Shashank Shrivastava from School of Engineering and Technology, IGNOU. In continuation with the previous module, this is the second module on smart materials topic, and here Professor Bhalla shall discuss about the futuristic application of smart piezo sensors.
Let us now come back to the lecture. Here we compare the typical signal of piezoelectric patch with accelerometer. So you see here one reinforced concrete beam. This beam has two types of sensors, accelerometer and piezoelectric patch embedded inside in the form of concrete vibration sensor or CVS. We are hitting the beam with hammer. This is the response from the accelerometer. We compare it with the response from the concrete vibration sensor, which is based on piezoelectric patch. The two responses, they have comparable signal to noise ratios and they are truly representing the dynamic behavior of the structure. Of course, accelerometer is giving response in terms of acceleration, whereas the piezoelectric patch is giving results in terms of the strain. But if we go in the frequency domain, we can use any of the two. Now if we compare from cost point of view, the typical cost of an accelerometer is in excess of US $500. At the same time, it's bulky and suffers from bandwidth limitations. On the other hand, typical cost of piezoelectric patch varies from US $2 to 10. This can be bonded on the top of the beam or it can be inserted inside using CVS. Of course, the special types like CVS, Duract and MFC, they are really expensive, but still they are much cheaper as compared to accelerometer. Now if we have a member which is undergoing flexural vibrations, this could be say a beam, then we can use a combination of piezoelectric patches, one bonded on the top, one on the bottom, and connected in an intelligent manner so that the combined voltage across the two gives us a measure of the top and bottom strains added together. Now this top and bottom strains added together is basically a measure of the curvature. So this provides us a venue of measuring the curvature. So curvature is something very important parameter as far as damage detection is concerned, because curvature is inversely proportional to the flexural rigidity EI of the beam. So any reduction in flexural rigidity owing to damage will lead to increase in curvature at that particular location. So all we have to do is we have to obtain mode shapes, the curvature mode shape before damage and after damage, and we can very easily find the location of damage. If we use accelerometer in the process, we have to do a lot of computation because we get the data in terms of displacement, which we have to do numerical differentiation in order to get curvature. But in the case of the piezoelectric patch, we can obtain curvature directly. So we use a process which is called as experimental modal analysis to obtain curvature mode shape. So what is experimental modal analysis? Experimental modal analysis means that we subject the component to vibrations, and in this process we obtain characteristic mode shapes and natural frequencies. We can use a typical shaker for this purpose. Shaker is given input by a function generator and we can give it input in the form of a sweep signal. So sweep signal means that the signal is passing through a range of frequencies starting from a lower value to a fixed higher value. So in one go we can subject the beam to these frequencies and we can measure the response. The other option is use a combination of impact hammer and sensor. So usually the sensors used are accelerometers, but we can replace these sensors by piezo patches. So typically we measure frequency response function, which is the ratio of the response to the applied force. So in the case of accelerometer, the response is acceleration, but if we are using piezo patches, then that too in combination in the flexural members with one at the top, other at the bottom and combined together, then we get the curvature. So this process helps us in obtaining the curvature mode shape directly. So what we have used is we have used the piezo patches as dynamic strain sensors and finally obtaining the curvature mode shape. So curvature mode shapes in this way, they can help us in finding the damage location. For example, here we see that there is a damage in the beam and the result of the damage is that curvature has substantially increased in the region of the damage. So this curvature is basically the curvature mode shape. So it helps us in finding the location of damage. Let us now go to the second use of the piezo patches in the form of electromechanical impedance technique. So here the PZT patch plays an active role. Active role means that it is used as an actuator also. In the previous application, it was just acting as a passive element that is measuring strains, but here it is acting very actively. It's being used as actuator as well as sensor. Second difference is that here the frequency range is very high, typically in the kilohertz range as compared to the previous application. So typically here what we do, we bond the PZT patch on the structure and then we excite it by applying an electric field. So typically we apply 1 volt root mean square using a device called as LCR meter, and this process makes the piezo patch undergo vibrations. So these vibrations, they are transferred to the structure. So basically we form a dynamic system consisting of the PZT patch and the host structure. So it is an electromechanical system now, whereas the PZT patch influences the structure also influences the PZT patch. So here the current flowing through the circuit, it is very much dependent on the structure. So we measure the current flowing through this circuit. So this current is coming on account of the direct effect, that is the sensing effect. So when we measure the current flowing through the circuit and find out the ratio of the current and the voltage, so here we measure the phase also. So the current will definitely have phase difference as compared to the applied voltage. So we get the resultant, the ratio of the instantaneous current to the instantaneous voltage as the admittance. So admittance has two components, G and B. So admittance is basically the ratio of current to voltage. So we have been familiar with impedance, which is the ratio of the voltage to current, but that does not make much difference. So the real part is called conductance, the imaginary part is called susceptance. So here in this particular application, the PZT patch acts as both sensor and actuator simultaneously. It should be noted that the technique was originally developed for aerospace structures, but now it has found applications in a lot of fields. So typically the device LCR meter is used in this process. It applies a voltage signal across the PZT patch, which is bonded to the structure, and it obtains the admittance at a particular frequency. So basically it applies a sweep signal and it scans through all the frequencies in the frequency range we desire. So if we just collect all these measurements, we get signature. So typically we can obtain both the conductance and susceptance plots. So it appears that the conductance has more interaction with the structure in direct sense, that we see peaks. So peaks are basically the resonance frequencies, whereas the peaks, they are less dominant in the case of susceptance. If we use both conductance and susceptance together, then we can do better identification of the structure and damage quantification. Otherwise, susceptance is a very useful measurement if we want to know the condition of the PZT patch itself. So it's used in diagnostics. So if we find that there is no change in signature, that means there is no damage in the structure. So signature is just like a fingerprint. So as long as the structure remains intact, the signature does not show any change. So this will give us the indication that structure has not undergone any damage. But the moment there is any damage, even if it's a very small damage, then we will immediately see change in the signature. Now why this is very sensitive? It's sensitive because we are using very high frequency. So high frequency generates very small wavelength, and these are very much sensitive to incipient damage. So typically this equation relates the admittance with the structure parameters. So here most of the other parameters are already defined. Omega is the angular frequency here. WLH are the PZT dimensions. So Z is basically mechanical impedance of the structure, which is the ratio of the force to velocity. ZA is the mechanical impedance of the patch defined in similar terms, and kappa is basically the wave number. So here there is no frequency limitation. We can use high frequency, so it ensures high sensitivity. So this equation tells that if there is any damage, so damage means the mechanical impedance of the structure will undergo change, and this change will lead to change in the admittance value, which is seen as damage. Let's now go to the lab and see in detail the measurement systems for EMI technique. So LCR meter is in general very expensive, but our students, they have made in the laboratory a low cost version by integrating simple function generator with a digital multimeter. Let us now come back to the lecture. The 1D equation can be further extended to 2 dimensions. So this is the equation for 2D electromechanical impedance. So what we see here in the denominator, we see here the Poisson's ratio, and instead of the normal mechanical impedance, we have the effective mechanical impedance of the structure. In fact, Professor Sumedha Maurana, she will cover in her lecture, which will be the last lecture post lunch, the detailed modeling. So you will be able to go through the mathematics part of modeling also in that particular lecture. Here we are just presenting the equations. In fact, she will cover with bond layer also. Now coming back to this equation, now this equation can help us in obtaining the mechanical impedance of the structure from the measurement. From measurement, we are obtaining G and B. So by use of this equation, we can obtain the mechanical impedance of the structure. Now mechanical impedance of the structure holds detailed information about the structure. So from the variation of the mechanical impedance of the structure, the way the real and imaginary parts vary, we can conclude what type of structure is it. We can find out the parameters. So this forms an impedance based identification. So this holds new information about the structure. In a particular frequency range, the structure can be identified as combination of basic elements. Those basic elements can be computed. Then the next thing is that how do we use these basic elements? So basic elements, they undergo change when the structure undergoes damage. So we need to calibrate these with damage. So we show here the example of fatigue life assessment of steel joints. So basically fatigue is a phenomena which occurs not just in civil structures but also in mechanical systems like machine parts and aerospace structures. So here PZT patches, they were bonded on these lap joints and they were subjected to fatigue damage. So this was a very detailed experiment. So the identification of the structure in this case was a parallel combination of spring and dammer. So the spring constant holds the promise here. In general, in case of fatigue, we can monitor fatigue damage if we determine the in situ stiffness of the component. However, this is the most difficult part. Now here PZT patch helps us in finding the stiffness by means of the identification. For example, here we are plotting the imaginary part with inverse of frequency. So This shows that the slope is a measure of the stiffness of the component. So what we find here, that as the number of cycles they are increasing, we can see that the slope is reducing. So that means the stiffness is deteriorating. So what is this stiffness? It is provided by the bonded PZT patch, sort of damage calibration. For example, here we have done damage calibration in the laboratory by number of tests. So we have basically evolved an empirical equation between the PZT identified stiffness loss and the remaining life. So once calibration is done on a small scale in the lab, this can be used in the real life. So this is one of the applications of the identified piezo based stiffness. Professor Visalashi Talakokula, she will cover more applications involving rebar corrosion, and that will be more interesting. So let's now go to futuristic applications. The PZT materials, they have a lot of futuristic applications in aviation, aerospace, in structural health monitoring. When we say structural health monitoring, it's not just restricted to civil structures, but it is extended to mechanical systems, aerospace systems, and even instrumentation engineers, they are also involved. It's also relevant for vibration energy harvesting and in the biomedical sector. So when we talk of the technological development, in general, technological development is organized on a scale of 1 to 9. So typically, when we conceive something and then we do laboratory experiments, that can raise the technological readiness level to level 4, that is integration level, showing system functions in the laboratory tests. Then from technological readiness level 5 onwards, we need industry collaboration. So this kind of collaboration between the academics and industry, it helps in the other further transition of the technology to level 5, 6, 7, 8 and 9. So level 7 is the demonstration of the complete system prototype in an operating environment. So if we talk of the structural health monitoring, the global structural health monitoring market is bound to grow to $4 billion by 2023, that is 3 years from now. So it has potential applications in civil, mechanical, aerospace and defense sectors. So what is important here is the integration of the sensing, data acquisition, data processing, inferencing and wireless capabilities. All these, if they can be brought together in a single chip, then that is the demand of the market. The other demand from the market is ultra miniaturization of the interrogation devices so that they can be clubbed together with the sensors. In the energy harvesting sector, we need power to run our sensors for structural health monitoring, our biomedical applications, our interactive control, or environmental monitoring. The next lecture by Professor Naveed Kaur, that will be a detailed lecture on piezoelectric energy harvesting using piezo materials. So piezoelectric energy harvesting market is also projected to be over $800 million by 2023. So all the startups which plan to work in this area, they have a very good future. Futuristic energy harvesting means that we will make energy harvesting as an integral part of our daily life. As the newer and newer devices are coming and they are demanding less and less power, so the future of piezoelectric energy harvesting is becoming brighter and brighter. We just show you a real life experiment where we have demonstrated the technology readiness level up to 7 for possibility of energy harvesting. This is a steel girder bridge just located in front of IIT Delhi. We took permission from the authorities to perform experiments here. So this is the typical vibration signal of the bridge, which shows that the fundamental natural frequency of the bridge is 4 Hz. So we now take you to the field and show the actual measurement. Piezo materials have futuristic applications in biomechanics also. Biomechanics is basically a multidisciplinary field. It entails application of the principles of mechanics to study the structure or function of biological systems. There is a very high potential for extension of all structural health monitoring technologies to the biomedical engineering field. This particular field is called as biomedical structural health monitoring. We show you one particular technology development which we have done till the readiness level 4. So this is at the laboratory scale only. So here we use the electromechanical impedance technique to detect osteoporosis. Now here the main issue is that unlike structures, we cannot bond the piezo patch, for example, directly with the bone or the skin. So we have come up with a non-bonded piezo system, which we have first tried in artificial bones and then did a proof of concept application on human arm also. So this part will be covered in one of the future workshops. So this is just to show that there is an immense scope of startups and applications of the piezo materials and the related technologies in biomedical sector. Now let us have a look at what is in future for newer piezoelectric materials. As of now, PZT is the most widely used piezoelectric material, but the problem is that its constituent lead is highly toxic and therefore it is an environmental hazard. A good substitute is sodium potassium niobate, which is a lead-free piezo material. But in the future, graphene is all set to revolutionize the application of piezoelectric materials. So graphene is basically a single layer of carbon atoms in hexagonal configuration. So this imparts it very high strength, typically more than 100 times that of steel. It also imparts it super high electric conductivity. So that means that the electronics which is based on graphene will have very low power requirements. It will also lead to the development of products such as foldable digital papers and thin electronics. Now, what is the application of graphene to piezoelectric effect? The application is that if a single layer of graphene is applied on the top of silicon dioxide grating substrate, then piezoelectric behavior can be activated by the chemical interaction of the carbon layer with the underlying silicon dioxide layer. The piezoelectric strain coefficient of graphene based piezoelectric material is very, very high as compared to the normal PZT material. So in conclusion, we have gone through this lecture and we have understood the basic working principles of smart materials, in particular piezoelectric materials. We have seen newer applications in structural health monitoring and futuristic applications in various domains. They are also envisioned. Piezo materials and all the related technologies, they have high potential for commercial ventures and startups. So if you want to study more about the applications of the piezoelectric materials, then we have this reference or book. This book also has an Indian version, so you can find all the coverage in detail here. Also, we have a number of references. These references can also be used. In addition, I would like to invite every one of you to our virtual lab. So this is an initiative of MHRD. So virtual lab helps in learning concepts by means of simulations. So there are simulation based experiments which you can conduct. You can go to the main web page of the virtual labs, www.vlab.co.in, and you can then go to our lab, Smart Structures or Dynamics lab, or you can go directly to our lab by ssdl.iitd.ac.in/vssdl. It will be a good use in the lockdown period. A number of resources in YouTube you will find very much useful.
So in this session, we saw that Professor Valla gave you ample information about the piezoelectric sensing and actuating effects, along with comparison with other similar devices like the accelerometers. Also, modal analysis and future applications of piezoelectric materials for energy harvesting and biomedical health monitoring were also discussed. From now onwards, we will move to the block number 2 of the material science course. We have finished the block number 1, which comprised of 4 units. Thank you very much.